Yeah, my name is Guy. I'm head of training at ScyllaDB. Feel free to say hello in the chat window and where you're from, just so I see that I'm not talking to myself. So this is me. I lead the training at ScyllaDB. I'm a software engineer and I'm based in Israel. And what I'm going to talk about today is the topic is denormalization and how that's done in NoSQL database, specifically wide-column databases. But to actually talk about that, which is a more advanced topic, I would have to start with some intro, some basic concepts in architecture, and also talk a bit about basic data modeling. So I'll do that first. Yeah, this talk is live. It's happening right now. It's not pre-recorded. So I would like it to be as interactive as possible. Yeah, so feel free to ask questions in the chat window. Tell me if I'm going too fast or too slow. Yeah, just say hello. And with that, let me get started. Yeah, so if you can chat your drink and your location. In the chat window, I am drinking water and I am right now in Tel Aviv, Israel. Yeah, so before I get started, I want to invite you to an event that's happening in 2 days. It's about real-time write-heavy workloads. Let me paste the link in the chat window. So it's an online event. It's free to register. All you have to do is register and you can join. And I highly recommend it if you're looking at a write-heavy performance-intensive application. That is, you need high performance and you have a lot of data. Okay, so the topics that I will be covering today are also covered in ScyllaDB University. That's at university.scylladb.com, and that's our online resource and training center. You have a lot of lessons, quizzes, labs available there. And as opposed to this event, which is live, the material on Scylla University is pre-recorded. And again, it's free. If you want to get started, all you have to do is register for a user and get started. And we also have our documentation website at docs.scylladb.com with more in-depth material, articles, manuals, and so on. So if I talk about something, maybe it's too fast, maybe I mention a concept that I don't have time to explain, you can check out these two resources to learn more. Great. So I'm going to start with some overview about NoSQL databases in general and specifically about distributed databases. So this is the CAP theorem. I'm assuming most of you are familiar with it. And the CAP theorem states that with distributed databases, we have 3 attributes we try to optimize for. However, there's a trade-off, like in so many other things in life, and we have to pick 2 out of the 3. So the 3 are availability, consistency, and partition tolerance. Availability means that no matter what happens, we will still be able to serve requests. Consistency means that, well, one definition is that for every read, we will get the latest write to the database. And partition tolerance means that even if there's a network failure, the database can still function. And I put some databases here on this triangle. And you can see that ScyllaDB together with Apache Cassandra and Amazon DynamoDB gives a preference to availability over consistency. Other databases like MySQL give a preference to consistency. And there are many others, and this is just an example, but that's one way to classify NoSQL databases. The focus of my talk today will be on wide-column databases such as ScyllaDB, Apache Cassandra, DynamoDB, as well as some others. An extension to this theorem is PACLC, which talks about latency versus consistency. So it says that in addition to those 3 things, If there isn't a network failure, then we have to consider a trade-off between latency and consistency. So if we want to achieve higher consistency, we would have to pay with latency. And ScyllaDB, as well as Apache Cassandra and DynamoDB, give a preference to latency over consistency. Okay, so some of the attributes of ScyllaDB. High availability, I mentioned that. So it's a distributed database. Data is replicated to multiple nodes. And that means that there's no single point of failure. Even if a single node or multiple nodes go down, the database can still serve requests. It also works with multiple data centers in multiple locations. The system is highly scalable, and that means that we can add and remove nodes without any downtime. Let's say Black Friday is coming up and we're running an e-commerce website. So we can very easily, a few days in advance, as we're anticipating having to serve more requests, we can increase the number of nodes. The database would automatically stream the data and balance the data between the different nodes. During Black Friday, we would be able to serve the more queries that are performed. And maybe after Black Friday, we can scale back down. And all this is done without any downtime. Next is performance. So the database achieves very, very low latencies. I'm talking about single-digit milliseconds. And it's also built for large data. Think about many terabytes. Low maintenance, especially if you're coming from an Apache Cassandra background. So it's written in C++. It has auto-tuning mechanisms, and you don't have to worry about garbage collection. And I mentioned Cassandra. So ScyllaDB is a drop-in replacement for Apache Cassandra and for Amazon DynamoDB, meaning that if you have an application running with either one of those databases, you can simply switch the underlying database to ScyllaDB and get better performance, more consistent performance, and also a lower total cost of ownership. So I mentioned low latencies, and we have an example that you can run with just a few clicks on your own, running 1 million operations per second on an I4I large machine. And if you click on this demo, you can run it on your own, and you see amazing latencies here. By the way, I'm going to be sharing the slides with you. So you don't have to worry about the links or, I don't know, copying things down. I'll share the slides with the links after today's event. Okay, so ScyllaDB comes in 3 different flavors. It's open source software, community-based. If that's your thing, you can hack around, add features, play with the code, compile it yourself. And there's a link there to the GitHub repo. Another version is the enterprise version. The enterprise version is more stable. It includes different features that are not part of the open source, and it also has better performance. And if you're running an application in production that's mission critical to your company, then that's probably a good option for you. You also get our support 24/7, and that's important. And last but not least is ScyllaDB Cloud, which is our database as a service offering. And with ScyllaDB Cloud, basically, we take care of running the database for you, so you can focus on your core business, which is probably not running a database. With ScyllaDB Cloud, we take care of upgrades, performance, security hardening, backups, restores, repairs, and so on, so you can focus on your application. By the way, you can run a free trial with just a few clicks on ScyllaDB Cloud, so you can check that out. Okay, I'll start by going over some basic architecture in ScyllaDB. Again, feel free to tell me if you already know this in the chat window, or if this is new to you, if I'm going too fast or too slow. So, and also, of course, to ask questions. So the basic architecture, the basic concept is a node. A node is something that I already mentioned a few times. I never said what it was, Basically, it's the Scylla software running on a server, on a machine. It consists of shards, virtual CPUs, and each node contains a portion of the database content. As a side note, relevant to almost everything that I will say today, the things that I'm talking about, I'm using ScyllaDB as an example, but they're also relevant for other wide-column databases, such as Apache Cassandra, Amazon DynamoDB, and others. Okay, so data is distributed across the different nodes, and this is how a cluster looks like. A cluster, we think about it as a ring, and it's a collection of nodes that work together to provide service. In this example, we have 5-node cluster. In production, the minimum requirement is to have 3 nodes, and we have some clusters in production running with hundreds of nodes working together. So the number of nodes depends on your specific use case, on your application, on your usage, on your performance requirements, amount of data, and so on. As I've said, high availability in mind. There's no single point of failure. All the different nodes can serve requests, and we have redundancy built into the system. So all the communication between the nodes is done peer-to-peer, and there's no single point of failure. All the nodes can serve requests. We don't have the concept of leader-follower or master-slave, or however else you want to call it. All nodes are created equal. Okay, I mentioned that data is replicated in the database, and that is determined according to something called the replication factor, and that is a setting that you as a user can set. The replication factor determines the number of nodes where data are replicated. Now, this is done automatically by the database, and it's set for something called a key space. A key space is a container of tables. And if, for example, we define a replication factor of 3, then looking back at our 5-node cluster, it would mean that each piece of data would be replicated 3 times. So if I write this row, say orange cube, it would be copied to 3 different nodes, okay, because the replication factor is determined as 3. And so on for other data. Each piece of data would be replicated to 3 different nodes. Okay, if I set the replication factor to 4, it would have been 4 nodes, and so on. So there's a question, is this a leaderless architecture? And that's correct. This is a leaderless architecture. It's more nuanced than that. So in recent versions, we have an implementation of the Raft consensus protocol, which ensures higher consistency. And then we would have consensus based on the Raft protocol, which designates a single node as a leader for a specific operation. But it would still be considered leaderless because we don't have a single point of failure. And the Raft mechanism works on a per operation basis. And the underlying technology used in ScyllaDB. So yeah, that's a big question. Basically, we're based on DynamoDB and the Big Table paper published by Google, I believe, in 2007. The result of that was Apache Cassandra, which is an open source database that's very popular and commonly used. And ScyllaDB was originally based on Apache Cassandra, but with some differences. So you can think of it as a next generation Cassandra, or that's how it originated. So Cassandra is written in Java, whereas ScyllaDB is written in C++. And it's written very much more close to the hardware than Apache Cassandra and saves a lot of maintenance. And basically, if we compare to Cassandra, we achieve usually times 5 or even times 10 the performance when we compare to Cassandra. And you don't have to take my word for it. You can go to our website and look at some benchmarks from some real world use cases where users migrated from Cassandra and switched to ScyllaDB, and they got some amazing performance improvements while using much less nodes. Okay, moving forward, data is replicated. Now, the things that I'm showing you right now are things that happen under the hood when data is written. So as a user, you don't have to worry about this. This is what the database does. But it's important to understand these concepts, to understand the basics of data modeling, which would take us to denormalization, which is the main topic of this talk. So under the hood, we define a partition key. So each table needs to define at least one column as the partition key. In this case, we have a simple table with 3 columns, pet chip ID, time, and heart rate, and the partition key is defined as the pet chip ID. Now, what the database does is when a user performs a query, writing a single row, the database takes the pet chip ID, the partition key column, and it performs the partition hash function on that column. And according to the given hash or to the given token, it knows which nodes are responsible for this specific piece of data. Okay, so the partition is really important. And let's go over some other concepts in data modeling. So we have a key space. I showed you how that works before. A key space is a container of tables, and it determines key settings like the replication factor. Within a key space, we can have many tables. Each table has rows and columns, and it defines concepts like the primary key, which includes the partition key and the clustering key. Another important concept is the consistency level. So ScyllaDB, together with Cassandra and others, has something called tunable consistency, which means that the consistency can be set per query. Okay, so we might have one query that requires a higher consistency, whereas another query in the same application would require lower consistency. So that's completely up to the user to set that up. And the definition of the consistency level is the number of nodes that must acknowledge a read or a write request. Okay, some examples are quorum, one, or all. Okay, and maybe an example of this. So if we have a 5-node cluster and we have a replication factor of 3, so yeah, let me go back to this example. So let's look at this. We have a 5-node cluster. We have a replication factor of 3. Each data is replicated to 3 different nodes. Now, if we perform, say, a read query trying to read this orange cube data, then if we define a consistency level of quorum, then that would mean that a quorum out of the replicas, which would be 2 out of the 3 replica nodes, would be required in order for the query to be successful. Okay, so 2 out of the 3 nodes need to acknowledge this query for it to be successful. That means that even if one node is down, say there's a hardware failure, the query would still be successful because the 2 other nodes would respond to that query. And again, for the exact same query, if we define a consistency level of all, so we would have higher consistency because 3 out of the 3 replica nodes would be required to acknowledge this query. However, there would be a trade-off with the availability, because if one node is unavailable, like I just gave in the previous example, then the query would fail, right? So we would be trading off higher consistency for lower availability. And by the way, in Scylla University, there's an entire lab called the High Availability Lab, and it demonstrates what happens when we read and write data with different consistency levels while simulating situations where some nodes are unavailable. So maybe I'll share that link as well when I send you an email after the event. Okay, so there's a question about the difference between a partition key and a clustering key. And that's a good question, but I'm going to keep it for later. So I think I'm going to cover that when I talk about data modeling. But if I don't, please remind me and I will answer that question. That's a good question. Okay, so I mentioned that a cluster has multiple nodes, and the nodes can be located in different locations and also in different data centers. Now, ScyllaDB is built to be topology aware, and that means that it knows about the topology and about the location of the different nodes in different data centers. Okay, so we can use multiple data centers, and that makes sense for different purposes. One would be, again, for availability. So even if an entire data center goes down, it's very unlikely, but it can happen. Then we would have redundancy. Again, say the EU data center comes unavailable, we would still be able to serve requests from the US and the Asia data center, for example. Another reason might be for regulatory reasons. So maybe in some geographical location, we're required to keep all the data of the users in that specific location. We can do that by using multiple data centers. And another reason would be for performance reasons, right? So it would make sense to serve a user, say from Asia, serving requests from the Asia data center and not from a data center in the US, for the simple reason that it takes time for data to travel from the US to Asia, right? So just for performance reasons.
Guy, you have some questions in the chat.
Yeah, I think I answered all of them, but I'll take some more later. Thank you.
Okay.
Okay, so this is an example from one of our users. I believe it was kiwi.com, and there was an actual fire in one of the data centers. I think it was OVH Cloud. And yeah, a lot of websites went down. This was somewhere in Europe. But because they were using multiple data centers with ScyllaDB, yeah, they remained available and they had no downtime. So that's just an example. And if you're interested in that, I think we wrote a blog post, or they wrote a blog post about this and what happened there. Okay, so I've been talking for quite a while. Maybe make sure you're still with me with a quick poll question. So the question is, what's your experience with ScyllaDB? And if you can quickly answer in the chat window, it's the first time you hear about ScyllaDB. Maybe you heard about it before, but you never tried it. Or maybe you're evaluating it, playing around with it, or maybe you're running it in production. So if you can quickly answer this question in the chat window, would be nice to see that I'm not talking to myself. Thank you. So the question is, what's your experience with ScyllaDB? You heard about it, but you never tried it, or you've never heard about it, or you're evaluating it, or you're running it in production. Okay, thanks for answering. Yeah, and let me move forward. So the next part is basic data modeling. Again, that's not the focus here, but to reach denormalization, I have to explain some data modeling concepts. This is an important slide. So it's a comparison of how we create a data model or do the data modeling process in relational databases versus NoSQL databases. And typically in relational, we first of all think about our data. We think about the different entities and the relationship between those entities. Usually we create an entity diagram, then we create our model or the schema itself. And finally, we think about our queries and the application. So this is the process for relational. And I'm mentioning this because many people have experienced this, or that's what they learned in university. And in NoSQL, we have to change our thinking a bit. And this is done a bit differently. So when we think about creating a data model, we think about the data at the very beginning, but we also think about our application. Okay, this is also sometimes called query-based data modeling. So we have to think about the queries that we're going to perform in our application at the very beginning, okay? And this is also very relevant for denormalization, which I will get to in just a bit. So we think about our data, we think about our queries and the application, and from that, we derive the data model. Okay, so this is how our data would look like on the disk. So I mentioned that for each table, we have rows and columns, and each table defines a partition key. In the example that we saw, the partition key was the column PetShip ID. Okay, so data is ordered according to the partitions, and for every given partition, we have our rows and our columns, which are basically just key value pairs. Okay, so that's how the data looks like on our disk, on our nodes. Now, I got a question before about the clustering key, and that's a good question. So I mentioned that each table defines a primary key. The primary key has two parts. The first part is the partition key, which I've talked about so far, but the second part is the clustering key. By the way, the clustering key, that's the name used in ScyllaDB and Apache Cassandra. In DynamoDB, it's called ordering key, okay? And ordering key is probably a better name, but we use clustering key, just because of our Cassandra background. So what's the clustering key? A clustering key is one or more columns that can be defined. It doesn't have to be defined for a table. And for a given partition, in addition to the partition key, our data would be sorted according to the clustering key. Okay, so if we define the clustering key to be the time column, then for a given partition, if we have multiple values, those values would be sorted according to the time. Okay, and that allows us to query the data according to the partition key and also according to the time, to the clustering key, in a very efficient manner, right? Because the database knows exactly within O of 1, within just performing the partition hash function, where exactly on which replica nodes this partition exists, where's this partition, because it simply has to perform the hash function. And then within a given partition, data is ordered according to the time, so it can very efficiently query the data. Okay, so that's the clustering key. And that brings me to denormalization, but let's see if we have any other questions first. Okay, so there's a question, is ScyllaDB API compatible with Cassandra and DynamoDB? And the answer is yes. So there might be minor differences, but basically you can take your application as it is, if it's written in working with Apache Cassandra or with DynamoDB, it can work pretty much as it is with ScyllaDB. Okay, so you don't need to make any changes. And even drivers or other third-party integrations that work with Cassandra would also work with ScyllaDB. So the answer is yes. There was a question about heart rate. So heart rate is simply one of the columns that's defined in the table. In that case, it was an integer. There was nothing special about it. It wasn't part of the partition key or part of the clustering key. And maybe when I talk about denormalization, I'll show what happens when we want to query according to one of those columns. Okay, so there's another question about data modeling for key value. So for key value, the data modeling becomes much more simple, I would say, because we simply have a set of keys and values, and we basically don't have the concept of rows and columns as in a wide column database. So on the one hand, that simplifies the data model. On the other, there are many things that we can't really do, and that also affect the performance if we compare key value to wide column databases. Okay, so that brings me to denormalization. What is denormalization and why do I want to talk about it? So in relational databases, we talk about normalization. We do things like performing joins on multiple tables. However, in NoSQL databases such as ScyllaDB and Cassandra and so on, we don't have the option to do a join. So we have other means to denormalize the data and to maximize performance. Now, what does denormalization mean? It means that we create a new table to serve a specific query. Now, this table can contain duplicated data. Okay, so that brings me back to this slide. And it means that I mentioned that I think about the application at the very beginning. So I think about the queries. And according to the queries, I create my data model. So if I know that I have a query that requires a specific set of columns, ideally, I would have a table that has those columns in my database. Okay, and that would go together with high performance. So when I perform the query, all my data is in that given table, and I don't have to start to look for it in a very inefficient manner. So one way to do denormalization is to do it at the application level. And that means that the user, whoever writes the application, can take care of maintaining multiple tables with all the data that we want to have according to the queries. However, doing that is both complicated, it's a lot of work in terms of the application, and it's also not very efficient. So in ScyllaDB, as well as in other databases, we have different mechanisms that allow you to denormalize data, and that means that the database takes care of denormalization for you. Now, let's see how that works. So I'm going to introduce pretty much 3 different ways to denormalize data and talk about each one. The first one is something called Materialized Views. What is a Materialized View? So Materialized View is a new table that's populated by a query running against the base table. So we have a base table, and we define a materialized view on the base table, and the database automatically takes care of updating the view according to what happens with the base table. Now, we as the application, as the user, can query both the base table and the materialized view. However, we don't need to and cannot update the materialized view directly. Now, let's see how that's created, or actually, what's the motivation for using this. So here we have an example of a table, very simple one. The table is called buildings. It has 3 columns, name, city, and height. And the primary key is defined as just 1 column called name. So the first one is the partition key. And when we query this table, we have to provide the partition key, okay? Otherwise, if you remember the partitioning hash function, the database would not know where our data exists and where to look for it. So if we perform this query, select from buildings where name equals something, then we provide the partition key. And if you remember what would happen, let me go back to the slide. What would happen under the hood is that the database would take that partition key, it would perform the hash function on the partition key, and it would know exactly which node and where within that node our data exists. Okay, so that's very efficient. But what happens if we want to query according to a different column? So let's say that from the same table, we want to query the table buildings, but we want to query according to the city. So if we do that, this query is going to fail. Okay, it's not going to work because we didn't provide the partition key. So that means that the database doesn't know where to look for this data, and it would be very inefficient. It would actually require a full table scan. So how can we overcome this problem? we can define a materialized view, building by city. And you can see here how it's defined. So we provide the primary key, which is the city, and then the name. And once we define this materialized view, what would happen under the hood is that the database would actually create a copy of our base table. It would copy the entire table, but it would look at the columns city and name as the partition key. And then we could perform the query that we saw before, where we provide the partition key of city equals New York. Okay, let's look at another example. So if we have a table called buildings, and this time our primary key has two columns, name is the partition key, and build date is the clustering key. If we do a select where we provide the partition key and the build date, which is the clustering key, then as expected, this would work. However, if we query according to the partition key name and the column height, which is not defined as the clustering key, this query would fail. So again, to overcome this, we can define a materialized view. And in addition to the name and height, we would provide the build year. And by doing that, this query would work. Now, to understand what's happening under the hood and when you should use this, keep in mind that basically the database is maintaining another table for us. So every change to the base table would be reflected in the materialized view table. And that means that we have to pay a penalty in terms of storage. So we need another table. And also whenever we update the base table, it takes more time because we're also updating the materialized view. However, the benefit is that reads are super efficient, right? Because when we want to read the data, it's already there in the materialized view, and that is very efficient. Okay, so let's see. I see there are some questions. So there's a question, if I have columns that need to correlate that are in two different column groups. So we can also, I hope I understand the question correctly, but if we have tables, we need to coordinate columns from two different tables. So then we can create a table that would include both of these columns. That would be one way. So it's sort of what we would do if we didn't have a materialized view. We would create a new table. And another option would be to perform two queries. Okay, so to query the different tables. I guess it depends on how often we're going to be performing that query and what are the performance requirements when we perform it. Okay, and I'll talk a little bit about that towards the end when I compare the different options. Okay. So another question is materialized view similar to other databases such as Oracle database. So the concept of materialized view, the name is maybe a bit confusing. It's different from SQL views. So from relational, it's completely different. Okay. Okay, so yeah, this is an example of querying. A query looks exactly the same, just that we query the table. That's the materialized view instead of the base table. And we can make changes to the materialized view. That's not very interesting. Okay, let's talk about the second option. The second option is secondary index. So a secondary index is another way for us to denormalize data. And let's see how it works. Let's look at an example. So again, we have a table. We have three columns, pet ship ID, owner, and heart rate. So this is the example we saw before. And like before, pet ship ID is the partition key, and the clustering key is the time. So that means that the first query, where we query according to the partition key, works. Yeah, I didn't mention it, but the clustering key is not mandatory. It's not mandatory to provide the clustering key. you can provide it. You can query according to the clustering key, but you don't have to. So here we're querying according to the partition key, and this query is going to work. However, if we try to query according to the owner, which is not either the partition key nor the clustering key, then this query is going to fail, right? Because, like I mentioned, the partition key is not provided. The database won't know where our data exists. It would have to do a full table scan and scan all the nodes to find this data. So this would fail, and we can overcome this by defining an index on the table. And this is the syntax to do that. So we create an index by owner on heart rate v10, which is the name of the table, and we define it as the owner. And then magically, we can perform the query that didn't work before. Okay, so now we can query according to the owner. Under the hood, a secondary index is actually implemented as a materialized view. Again, this is transparent to you as the user, but it's important to understand when you choose whether to use secondary indexes or materialized views. And basically, what's happening under the hood is when we define the index, we're creating a materialized view that sets the owner as the primary key with the other columns. So what would happen under the hood? I think I have a slide for this. So what would happen under the hood is that when we select from the table using the index, what the database would do is it would first of all look at the city and find the partition key from this materialized view. So there's basically a table with the index and the partition key. According to the given index, it would find the partition key, and then it would do an extra query using that partition key that it found. It would query the base replica to actually find the data that we're looking for. Okay, so it's a bit nuanced, but this is different than a regular materialized view because we don't create an entire copy of the data that we want to replicate or to denormalize, but we only create a table for the specific index. Yeah, I know this is a bit complicated, but maybe I'll explain the pros and cons of each one, and that will make it more clear. So if we choose to use an index, that means that we have to pay a lower price in terms of storage, okay? Because we're not replicating the entire table. It requires less space on disk. However, we pay in terms of performance, and specifically in read performance, okay? Because when we read the data, instead of having all the data that we're looking for in one specific table, now we have to do basically two hops. First of all, query the index table, and then after we get the partition key, query the base table. Okay, so we save storage. On the other hand, we pay the price in read times, and also writes would be cheaper, right? Because the write would have to update less data. So I know that's a lot. I'm going to summarize that in just a bit. Yeah, local secondary indexes are even more specific, I would say. And with local secondary index, which by the way, doesn't exist in Apache Cassandra, it's ScyllaDB specific, we get the promise that the data would exist on a specific node. So we don't have to go and search multiple nodes, but that's more advanced and it's a bit out of scope. Just know that it exists and you can read more about it, or yeah, look at the lesson on ScyllaDB University. Let's stop for a second and see what are the questions we have. So there's a question about using joins to create a materialized view, and that's not possible in ScyllaDB and other wide-column databases, it's impossible to do joins, and we have to define the materialized view, which actually saves us from using those joins. Okay, so instead of using the joins, we use the materialized view to denormalize the data. Another question is the materialized view created at runtime. So the materialized view, the way I think about it is it's just like any other table. It's created once we execute the command defining the materialized view. And from that point onward, we have an additional table. That's the materialized view. Now, after we define it, we don't really have to worry about maintaining it. The database does that for us. And whenever we're going to execute a query querying the base table, it's going to update the materialized view and keep it in sync. The difference is that now we can also query the materialized view. Okay, so we don't have to worry about updating the materialized view, but we can query it. Let's see if we have other question. So there's a question about write performance. I'm going to answer that in just a second. So there's a question about secondary indexes versus materialized view. It's not exactly a pointer list. Yeah, let me think about that. Well, maybe you can think about it as a pointer list. The way I like to think about it is a materialized view. It's actually implemented under the hood as a materialized view, but it's a materialized view that doesn't have all the rows in the base table. So it's a materialized view that only has the index and the partition key. Okay, so it's just a smaller materialized view. And because it doesn't hold the actual data that we want to query, we use the secondary index to query according to the index, find the partition key in the base table, and using that partition key, we then query the base table again to find the data that we're actually looking for. Yeah, and I guess you can think about it as a join, or yeah, we just don't use that term, I guess, to avoid confusion. Is this process done at runtime? So yeah, this process is done just like any other table, and it's done, the database takes care of it at runtime. So whenever I perform a query, that query is going to update the base table, but also update the materialized view. Okay, so this is something that happens at runtime, and it's completely transparent to you as the user. And in just a second, I'm going to show you the trade-offs between the different options. Okay, so again, there's a question about the storage, and I'm also going to try to answer that in the next slides. Okay, so this brings me to the last option, which is allow filtering. And after the allow filtering, I'm going to talk about the different options and compare them. Okay, so what's allow filtering? Basically, filtering allows us to query by non-partition key columns without creating a materialized view or without creating an index. How is that done? Do we have some kind of magic here? The answer is no, we don't. It simply involves doing a full table scan, and that can be very painful in terms of performance. So let's see an example similar to what we saw before. We have a table called buildings with name, city, and height as the columns. The partition key is name. Now, when we perform this query, select from buildings where city equals Brussels, city is not a partition key, and the database would not know where to look for the data, right? It doesn't have the partition key. It cannot perform the partition hash function, and it doesn't know where our data is. So when I perform this query, previously, maybe I wasn't completely accurate with what I told you, because I told you that this query would fail. But actually what would happen is that I would get this error message. And this error message says this query cannot be executed. It might have unpredictable performance. And if I want to override it, I have to use the allow filtering keywords. So maybe it's not really an error message, it's more like a warning. And the database is telling us, listen, you can perform this query, but if you perform it, we cannot guarantee the performance. It might be very slow because we don't know where the data is. We're going to have to scan the entire database. So if I add the keywords allow filtering, then this query would simply work. Okay. Now, when we use this, we have to, think about it and know what we're doing. There are cases where it makes sense to use allow filtering, and there are cases where it doesn't. Think of a big database, I don't know, having 60 nodes in our cluster with, I don't know, hundreds of terabytes, and using allow filtering might take a lot of time and take up a lot of resources as we're scanning all the table throughout the different nodes. We don't know where our data is. It can take a lot of time. Okay, so when should we use each? And I hope this is also going to answer the questions that we just saw. Okay, so to summarize, we saw 3 different options for denormalizing data. One was materialized view. That was the first one. The second one was secondary indexes, which had like a specific flavor, which was local secondary indexes. And the third option was allow filtering, which is actually a full table scan. When should we use each option? So conveniently, we created this flow diagram that gives us a hint of when to use each. Okay, so we start right here. And the first question we ask ourselves is, what is the read frequency? If the read frequency is very rare, say maybe we're doing this query once a week, and it's not very critical that we have a high performance, we can wait a bit with the results of this query, then maybe it would make sense to use allow filtering, right? Because that saves us having multiple tables, creating copies, paying a price in storage, paying a price in updating the materialized view or the secondary index table. So in that case, it would make sense to use allow filtering. And this is summarized here. We have 0 write path impact. So when we write data, there's no penalty. However, when we read the data, there's a huge impact. So we want to make sure that the read doesn't happen very often and it's not performance sensitive. So what happens if our read frequency happens often? Okay. If that's the case, we want to look at, I wrote here index cardinality, but maybe selectivity is a better way to think about it. So if my selectivity is low, meaning that I'm going to be selecting a lot of the rows, then again, it might make sense to use allow filtering. Why? Because if I have a query that is going to return a high percentage of my data, say it's returning, I don't know, 10, 20, 30% of the rows in the database, then it does make sense to use allow filtering, right? Because anyway, we're going to be scanning to return a lot of those rows. So if we're returning a high percentage of the rows, it might make sense to use allow filtering. And then again, we get the benefits of no impact to the write path. And we have to consider the performance requirements because it's going to take a lot of time. However, it might make sense because anyway, we're returning a high percentage of the rows. So the question is, shouldn't that say less than 1% of the rows are selected? Yeah, I actually think it's correct. It's more than 1% of the rows are selected. So maybe it shouldn't be low. Maybe it should be high here. So high selectivity. Yeah, I have to think about that. But the definition, or what I want to say, is that a lot of rows are being selected. Yes. So I do think it's low selectivity, because selectivity means like if we're very selective, if there's a high selectivity, then we're selecting a very low percentage of the rows. At least that's how I understand it. If we have low selectivity, then we're selecting a high percentage of the rows. And it makes sense to select that if we're selecting a high percentage of the rows and we're returning a lot of the data in the database anyway, then that makes sense to use allow filtering. So I think the 1% is accurate. I'm not sure if we have any benchmarks that test this, but that's a good question. I'll write it down and look into those numbers. Okay, so going back to cardinality, if the cardinality is high, which goes back again to selectivity, meaning we're not selecting a high number of rows, so we're having high selectivity, then we are going to look at two different options. One is if we want to give a preference to read latency. If we want a very low read latency, and low latency translates, of course, to better performance, then we want to use a materialized view. Now, if you remember, what happens with a materialized view is that we're duplicating a lot of the data. We're paying a price in storage and in writes, but we're getting the benefit when we do the read. So when we read the data, if we use a materialized view, we get those benefits. On the other hand, if we want to optimize for storage and we're ready to pay a price when we read the data, then we might opt to choose secondary indexes, and then we would save on storage, pay a price on reads. Now, maybe a small caveat or side note is that even when we use secondary indexes and have that extra hop, still we get amazing performance. So again, we're talking single-digit millisecond performance, and for most application, that works. Okay. So selectivity means being highly selective and only returning a small percentage of rows. I would use a different word, few rows selected. Yeah, that makes sense. I'll think about that and maybe fix the slide. So thanks for the feedback. Yeah, we're pretty much out of time. Again, two useful resources, university.scylladb.com, covering these and other topics. We have a community forum, forum.scylladb.com. You can ask questions. I check the forum. Other people from the community, our engineers, hang out there. So if you have NoSQL or ScyllaDB related questions, feel free to ask there. And that's it. Thanks for joining today. Like I said, I will send you an email with the link to the slides and to some of the labs maybe that I mentioned. And yeah, thanks for joining. Maybe I'll also send you a feedback form so you can also ask for other interesting topics for the next meetup that we can talk about. Thanks, everyone.